Why don't we get started? Like I said, I don't have anything new to cover today, but if you have any questions on, probably preferably on the material that's going to be on the fourth exam, the final during the final period, I will try to answer them now. Like I said, I think in the announcement it tells you explicitly which sections are covered, right? But it's basically chapters 8, 9, 10, 11, and 13. Okay. Oh, well, I'm sorry. 8, 9, 10, and 11. No, 8, 9, 10, and 12, right? 8, 9, 10, and 12. And then 13 is extra credit problem. Okay. The column buckling would be extra credit. Okay. So combined loading, stress and strain transformation, as well as beam deflection. Okay.
Can we go over maybe a beam deflection problem of your
Yeah.
choosing that you think is good?
Okay, so when we do beam deflection, let me go over to beam deflection real quick. There's two ways to approach that we've covered that we're going to approach beam deflection problems. Okay, and all right. So let's say I'll just pick a simple case. Okay. If you have a beam that's fixed at one end and then has some loading at the other end, of course, it could be anything like this, and you'll be given the parameters. One thing you can do is you could look for an appropriate beam table to support it. And in this particular case, there is one. If you go and look in Appendix C, I almost guarantee it is. This is in Appendix C. I don't know what I want to call this. It's the first case in the second table. Okay. You can use that. Okay. You can use that, right? There are cases where you might not find that particular case in the beam table. All right. You might have to do something if we had something like this. All right, this particular case.
Dr. Ches, I think we're not looking at your screen.
It says I'm sharing my screen. What am I sharing? Stop sharing. You see that?
Yes, sir. Yeah.
Yeah. All right. So let's go back. Let's do it again. All right. We'll go back and do it again. All right. So if you're given a problem as shown here, right? Cantilever beam fixed at one end, tip load, right? If you look in Appendix C, it's the first case in the second table is exactly this. And this will tell you the beam deflection V of X is minus PX cubed over 3EI, 6EI. All right, so that gives you the deflection. And obviously, if you need to figure it out the tip, you can put in x equal to L, and then, this just becomes minus P L cubed over 3EI. And that's a squared. This is a squared. Okay. Now, if you have something that looks like the following, all right, you will not find this case in the table, but you will see that there is obviously the tip load case plus the distributed load case. These are separately in Appendix C, right? And in this manner, you can use superposition, right? Right? So you can use superposition in that case. And, obviously you will get, if we call this case 1 and this case 2, you can take, say, the tip deflection of case 1 and the deflection at case 2, or wherever the deflection is, and just add those together, all right? And that works as well. You could possibly also have a situation that is sort of neither of those, okay? And these are where it can get kind of interesting. Let's say we have something like this. Now you could have this case, right? And I don't know, there's probably a problem like this. Maybe I should find a problem that looks like that. Now that does not exist in any of the beam tables. There is a trick where you can do it from some beam tables, but let's hold off on that for a second, okay? And I'll explain the trick in a second. It's very similar to the trick we did for statically indeterminate beams. I'm sure there's an example of this because there's really only so many beam deflection problems that exist. Yeah, okay. Oh, that's a little bit. Oh, let's do it that way. Let's do the one. Yeah, this is probably better. All right. So this is a problem in the book. This is 12.4. And this has no numbers, but that's fine. And obviously, the point load is right at the middle. So it's L on 2 on both sides. And you can assume a Young's modulus and obviously an I for the beam. And here they want you to find the elastic curve, V of X. All right, so now in this case, you really are going to have to do, well, one way is to actually do the direct integration. Remember, first we get the shear diagram, then we integrate that, and we get the moment diagram, right? Which we did previously under the beam stuff, so that's nothing new. And then we know that EI times the derivative of the slope curve equals the moment curve. All right. And then we can get that the derivative of the elastic curve is equal to the slope. Okay. So we do two more integrations. Out of each one of these integrations, you're going to have constants of integration. So we need to talk about boundary conditions. And not only that, because the point load's in the middle, you get a little bit of discontinuity. So we have continuity requirements as well. So we're going to have to do two integrations. So this is going to give you two integration constants. Just like when you solve differential equations, and we're going to use boundary conditions to do that. And then you also will have a continuity requirement on this one. Oops. And that comes about because when we look at the moment diagram, it's going to have a discontinuity right here at the middle, okay? And so you're going to have a moment on one side and, two equations, and the moment has to be continuous. It has to be C1 continuous at the midpoint, okay? And so we'd use that to pick another, to get the other relationships, okay? All right, so if you were to do that, all right, let's figure this out first, right? So first we have to get the support loads. Okay. So we got to get the shear and the moment diagram for this one, right? So, right. So obviously, let's do that one. So we'll call it A and B as the two ends, right? And then here in the middle, we have P. All right, so if we do sum of moments, I don't know, whatever. Oh, is this statically indeterminate? This is statically indeterminate. Ah, this is statically indeterminate. Oh, because the book, this one's pinned. Ah, I'm sorry. And this one, the book has this pinned. All right, so in the book, this is pinned. So now we just have this, okay? So in this case, it's pretty easy, right? FA equals FB equals P on 2, because it's the middle, right? So we know this case, all right? All right. So the shear diagram is going to look like this, right? Okay, so here's X. All right. So the shear force at A, if we go just a little bit to the right of A, the shear force is acting down to balance FA, right? If I take this sort of cut. So that is a positive shear force of P on 2. So we start off at P on 2. Then at the point load P, it drops down by a value of P, taking to be negative P on 2, and then back up here at point B, right? This is positive, this is a negative shear, and this is obviously minus P on 2. All right, the moment diagram is going to be as follows, right? So we integrate to get the moment diagram. There's no support moment at point A or at point B, so the moment diagram has to vanish at point A and point B. The derivative of the moment curve equals the slope, right? That's from the integration. So here we have a slope of positive P on 2 up to this point, and then a slope of negative P on 2 to this point, right? So this has a slope of P on 2, and this has a slope of negative P on 2. And so this value of the moment here, right? Right, it's the area under this curve, which is going to be P on 2 times L on 2. So that's PL on 4. All right, so that's the peak moment. All right, so if we were to write out the moment here, the moment as a function of position would be as follows, right? So the moment is going to equal P on 2x, and that's from 0 to L on 2, okay? And then from L on 2 to L, right, it's going to have a slope of minus P on 2, right? So minus P on 2. But then it has to go to 0 at x equal to L. So will that do it? I believe that'll do it. Yes. Okay, let me just double check. So if I put in L on 2 here, I get L on 2. Oh. Okay, this way. You got it there, right? P on 2, so it's a slope of minus PL on 2. If we put in L on 2 for x, I get PL on 4, which is the correct value, right? So this is right. So this is from L on 2 x to L, right? All right. Okay. So now what do we got to do, right? What are our boundary conditions we have here on the displacement and the slope? Well, it's pinned at both ends. So remember, when we're pinned, we know that the displacement at x equal to L has to equal the displacement at x equal to 0, and both of those are going to go to 0. It's pinned, so the slope is going to be non-zero, or definitely it's not required to be 0, right? So those are our two integration terms, all right? And then when we integrate it, we're going to integrate each one of these equations, so we're actually going to get integration constants from that, but those are going to be satisfied by continuity. All right, so let's integrate once. So, okay, I'm going to integrate this once. So M on EI, when I integrate it, this is going to give me EI times theta, okay? Right? Because remember, EI theta prime equals M, right? So we're going to integrate the moment equation. We have to integrate both of them. So I get P x squared on 4 plus an integration constant, B0. And then if we integrate the bottom equation, I get P on 2 L times x minus 1/2 x squared, right? So in fact, I can pull the x out of there if I want to, right? Same integration constants, right? All right, I'm sorry. And then I get plus an additional integration constant on that term, right? All right, so here you can see we've picked up two integration constants, right? And so we have the fact that the deflection goes to 0 at both ends, but this is the equation of the slope of the curve. So that this boundary condition here will not do me any good in solving those constants of integration. If I had like a fixed end, right, that might do me some good because I would know that theta equals 0, but I don't have that, so I can't use these conditions to do me any good. But we do know that we know that the slope, right, at L on 2 from the negative side has to equal the slope from the right side, right? It needs to be continuous. This function here needs to be continuous with regard to x. So I can use that at least to get one of these integration constants out of the way, all right? So let's do that. So if we look at this and evaluate it at x equal to L on 2, I'm going to get the following, and I'm going to write the two conditions top and bottom. So I'm going to get P L squared. So L on 2 gives me a 4. So this is 16 plus B0. And now if I put an L on 2 into the second term, right, this is going to give me P on 2 L squared on 2 minus L squared on 8, correct? And that's equal to, this is just 4L squared on 8, so 3/8 L squared, so 3P 16L squared. I'm sorry, I forgot the plus B1 plus B1, correct? And these have to be equal. Those have to be equal. We need to have continuity in the slope at L equals 2, all right? So right at the middle, we have continuity. So if that's the case, I can get that B1 has to equal what do we do? Yeah, I know both over, I guess it doesn't matter. B0 plus PL squared over 16 minus 3PL squared over 16. And so that gives me B0 minus 2 PL squared over 16 or PL squared over 8, right? So now basically what do we got? Now we know that EI times the slope is as follows. So now I have the slope curve with one integration constant. So PL squared over 16 plus B0, and that's from, let me see where it is. And then for the second one, I get, I'm sorry, what am I doing? It's this term up here, right? So it's px squared on 4 plus b0. And then this one here, I can pull the x out, whatever. It's actually easier to keep it this way for now. So p on 2, p on 4, 2lx minus x squared plus b1, but b1 we know is negative PL squared over 8 plus B0, right? And this is from L on 2 to L. Okay? All right. So now to get the deflection curve, we're going to integrate this again. So we're going to integrate. And then when we do that, right, we get EI times the deflection. And what do we get? Take the antiderivatives of this. I get P x cubed over 12 plus b0 times x plus c0, okay? And then for the second half of the beam, we're going to get p on 4. All right, this becomes lx squared, and this becomes minus x cubed on 3 minus pl squared on 8 times x plus b0 times x plus another integration constant, c1. All right. Okay. Now we have 3 unknowns, b0, c0, and c1. We know that v at 0 equals 0 and v at x equal to L equals 0. So that's 2 conditions. That can allow me to solve for 2 of those constants. But again, I have to have a third one, but I also have continuity. That v at L on 2 from the left side has to equal v at L on 2 from the right side, right? There can't be a discontinuity in the deflection, right? Unless the beam is broken, all right? All right, so what do we do? Well, these are actually usually pretty easy to do because everything drops out. Like there's X on everything. So if we put in the 0, if we do V, the order doesn't matter, right? But if you do V at 0 equals 0, I can put that into the first one, right? I can put that into here, and I just simply get that C0 has to equal 0. All right, so I got that one done. All right, the L one doesn't do me any good because nothing else goes away, right? All right, so I know C0 has to go to 0. All right, let's do the continuity one now. So now I've got P L cubed over 2, that's an 8. 8 times 12 is 96, right? 96 plus B0 L on 2, C0 equals 0. So that has to equal the right half of the beam. So I get P on 4, L on 2, that's L squared on 4. So I get L cubed on 4 minus L cubed. That's on 8 times 3 is 24, right? Minus PL squared times L, that's L cubed, and I get 16 plus B0L on 2 plus C1. All right. All right. In this particular case, the B0s cancel out, right? That goes out with that. Those cancel. So now I'm just left with C1. This becomes 6 over 24. So this becomes 5L cubed over 24, right? Times P on 4. So wait. He's always. So I got P on 4 minus PL squared over 16. All right, so 48. So this is 5 PL cubed over 48 minus PL squared over 16 plus C1 has to equal PL cubed over 96. All right, so 96. So this is 10 PL cubed over 96, correct? And then 16 goes into 96 7 times? Is that what it is? Oh, I hate this stuff. Yes, so 6 times. So this is minus 6 PL cubed over 96 plus C1, right? So I get this as 4 over 96, right? PL cubed. And then I bring that over to the left side. So it becomes minus 3, right? So I get C1 equals minus 3 over 96, which can reduce to something PL cubed, which is 3 goes into 96 32 times, right? PL cubed over 32 with the minus sign, right? All right, so now what do we got? Let's zoom back out, right? So I know, still don't have B0, but I know, what did I do? Where did I got C1. Okay, so now I've got C1. So I got C0 and C1. I just don't have B0 yet. So let me go over here and do this. I'm going to write it over to the right-hand side. So now we have V of X equals PX cubed over 12 plus B0 is still not known, and C0 is 0. And then down here, I have P on 4 LX squared minus X cubed on 3 minus PL squared on 8. X over 8 plus B0X plus C1, which we now know is minus 3 PL cubed over 32. Nope. It's minus PL cubed over 32, right? All right, so finally, we still need to get B0, and this is finally where we're going to use the fact that at X equal to L, it's pinned, so the displacement goes to 0. And so obviously that has nothing to do with this first equation because that's not valid at X equal to L. It's only at this second equation. So if we put in X equal to L here, what do I get? I get P on 4. Okay, whatever. L cubed, right? L cubed minus L cubed on 4 minus PL cubed over 8 plus B0L minus PL cubed over 32 has to go to 0. And we can solve for this for B0. So this is 3/4 minus, this is 3/4. So I get 3 PL cubed over 4, which is, I got to put it all over 32, I guess, right? Everything has to go to 32. So 32 is 8, right? 8 top and bottom. So this would be 8 times 3 is 18 over 32 minus 4 PL cubed over 32 minus PL cubed over 32 plus B0L equals 0. So let's get rid of one of these L's. So these all become squared, right? And what do I got here? I've got minus 4, minus 5, 18. So that's 13. And that's a positive, so that is equal to B0. And that's the final integration constant. I would almost guarantee I made an algebra mistake on this, but you know, I'm not responsible for those, okay? And that would go into here as well as here. And that would be your final answer, okay? So it's just, so, you know, you're always going to have two integrations. And like I said, if you have a shear diagram, like in this particular case, or I'm sorry, a moment diagram, where there's a slope discontinuity, right? You know, you're going to have a piecewise linear moment curve. Every time you have a piecewise continuous curve, you're going to get additional constants of integration, but those can be solved from the fact that the slope and the discontinuities, they need to be continuous, okay? They need to be continuous. All right, so that would be one way to do it. The second way to do it, let's look at this approach, and let's do the statically indeterminate problem. So this is a little more reasonable, right? I'm doing on time here. So let's go back and consider the original example that I had, right? This case where it's fixed. All right, and it's pinned on the right side. Again, let's put the load right here at the middle. So this is going to be L on 2, L on 2. All right, L on 2, L on 2. And EI. So same as before, but we just put we just made it fixed at the other end, right? Now, in this case, this is statically indeterminate. And that's because when we look at the free body diagram, we have three unknowns. We have the up force here, force at B, the up force from the wall at A, but we also have a moment at A from the wall. So I can only write two equations, sum of forces in the Y and sum of moments around a point, but I have three unknowns, right? And that's the three reaction unknowns. And so this is statically indeterminate, okay? All right. So how do we go about doing this? Well, you know, you can theoretically do the integration and then also supplement that with the additional term that it goes to zero, but it just becomes a real algebra nightmare. This is one where the assumed force method is kind of a lot easier. In this case, what we're going to do is we're going to consider the superposition of the following two cases. We're going to do this case. Fixed here with the load at the middle, which we do have a plot for, right? I'm sorry. There's a case for that in the beam table. Right? That I know. This is going to be case 1. And superimposed on that is going to be the following, where I have an up tip load here, and here I'm going to set this
equal, we usually set it to unity. You can actually set it to a letter value, but, just to keep things easy, I'm going to set this equal to unity. Okay. All right. And the idea here is I'm going to have to get this so that the deflection at L equals 0. So we're going to scale the unit force such that, right, we get that condition that the deflection at point B, x equals to L, goes to 0. All right. All right. So I don't have to integrate in this case. This is nice. So let's look this up in the beam table. So I know I have this case here. All right. So this is, I'm going to call it, this is case 2, right? Okay. So for case 1, well, this is kind of annoying. I should have flipped it. Case 1 is really the second case in the beam table, and case 2 is the first case, but so be it. Whatever. You can look it up. I don't think you guys be too challenged by that. And in this case, the deflection at the tip, right? The deflection at x equal to L, that's the max deflection. From the table, this is minus 5 PL cubed over 48 EI. All right, that's what that is. Okay, now on this case here, right? On this case here, so I'll put a little Roman numeral 1 superscript there to differentiate that. From the second case, right? I get the deflection. Now the force is going the opposite direction. So the deflection is up. I get P. Well, P is 1, so I get L cubed on 3 EI. All right. Okay. I would like this added to this to go to 0, right? Right? So how do I get these? They're already opposite sign. So what do I multiply this by? What's the factor I multiply this deflection from the second case by so that it equals the first case, right? So it's 5 over 12, right? No, 5 over 4. Oh, sorry.
16, I believe.
16, right, yeah. 5 over 16, right? Okay, so that means that really this whole second case needs to be multiplied by 5 over 16, okay? So this force here really should be 5p over 16. Does that make sense? Okay. If that's the case, then, actually I should put, right, because I should really have p here, right? Because I don't have p here, right? There's no p here, right? So, okay. All right. So fine. So now you know everything. Actually, if you go and look at these two cases, they also give you the end conditions, I believe. Do they? Oh, they don't in the table, but it's pretty easy to figure out. Okay. So let's do this. Let's be a little careful about this, right? So if we look at the first case, clearly the force acting up here has to be P, correct? And the moment, I know I should erase the end condition, but forgive me on that. All right. For the moment, so this is PL on 2, correct? And it goes the other way. That would be for the first case, right? Those are the support forces there. All right. On this one, we would have a downward force of 1. And then the moment, since this whole thing wants to spin to the right, it's going to be a moment that spins to the left. And the moment there is 1 times L. Okay? So when we multiply this all by 5p over 16, actually, the second case really becomes the following, right? This is the second case of forces, right? All right. Acting up here, I have 5p on 16. This means acting down here, I have 5p on 16, right? Because we multiply everything here by 5p on 16. And so the moment is going to be 5pl on 16. Okay? All right. So those are the two cases. This is case 2. This is case 1. All right. So just like we added the deflections together to get the net deflection, we have to do the same for the support loads. Okay? So what actually happens for this case, if we want to know what it is for the final answer, right? All right, where we have P at the middle, and we're fixed on the left side, and we have the roller deflection here like this, right? Now we know everything to solve this case. Okay, first let's get the reaction forces, right? So in this particular case, we know the up reaction force at point B is going to be the addition of the two cases. Well, there's no tip force at B in the first case, so this just becomes 5p on 16. And we have to add this with P on the left side, so that's a 16 over 16 plus 5. That is 21, right? And oh, I'm sorry, one goes up and one goes down. So this is 16p on 16, right? So we minus 5, so it's 11 going up, right? So it's a net 11 going up. So this is 11p over 16, right? And likewise, we have to add the moments. And I gotta make sure. Oh, this actually goes the other way. I'm sorry. This needs to go the other way. Okay. These arrows actually go this way because they're opposite sides. All right. So when we do the moments, right, we've got over 16. So this one here is 8pl over 16. And okay, that's the greater. So we're going to subtract the 3. So that means the net moment here is 3pl over 16, correct? So now we know the support forces. Okay, there they are. Let's say you wanted to get the deflection. Okay, so let's say we want to get the elastic curve. We know from the first case, okay, this case here where it's, the cantilever, I'm sorry, the first case, remember, is this case, right? For this case, the elastic curve is, what did I get in here? Oh, it's a pain. Okay, whatever it is. All right. The elastic curve for this case is, it's a split one. So I get minus, this is just reading right off the plot, minus x cubed over 12 EI 3L minus 2X. And that's from 0 to L on 2. And then the second half is minus PL squared over 48 EI times 6X minus L. And that's from L on 2 to L. For the first case, I'm sorry, for the second case, it's a little simpler. The deflection, the elastic curve for the second case, it writes it in the book as PX on 6EI, right? But remember, P is going to be the scaled by 5P over 16, right? Because it's not the unit force, it's the 5P over 16. So if I put that in there, it becomes 5P over 16 times 6. What is 16 times 6? 36, 96, right? This is 96 L, 3L minus X. And this is for the whole length of the beam, okay? Because really, if you look it up in the table, it's going to tell you that it's minus PX squared on 6EI. This is from the table, 3L minus X, okay? This is from the table. But remember, if you look at the table, that's the case where we have a downward force of P, but we actually have an upward force of 5P on 16, correct? So I put a minus 5P 16 in here for P, and that gives me the following, okay? And that's the deflection curve from 0 to L. It's the same. So the total deflection curve is just the sum of these two. So the deflection curve, the elastic curve, is as follows, right? 5P over 96, 3L minus X plus the following, minus PX cubed over 12 EI. I mean, you can write it twice if you want to. It's the same difference, but I'm lazy. Minus PL squared over 48. Fortunately, you usually don't need to get the full elastic curve. You usually only want to know the maximum. And now that gets a little bit weirder because when you do the statically indeterminate case, you have two different cases. The maximum might be at different points. So you can't necessarily add up the maximum, right? So be it. And that's it, right? And so this is from X from 0 to L on 2. And this is X from L on 2 to L. Okay? And that would be a statically indeterminate case, right? And I think you could always get a statically indeterminate case in terms of one or more combinations of the something that's in a beam table, to be honest with you, okay? I could have also, this problem here, the one where it was pinned, where I went through all the integration, right? This one. Let's say you're not a big fan of the integration. You don't like integration. I don't blame you. Algebraically, it's kind of a pain in the butt. I don't mind the integration, but I hate doing all the algebra of the integration constants, right? You could do this problem as well. It's not statically indeterminate exactly, but you could use the same approach we did for statically indeterminate. And that's actually, in a lot of cases, easier. So let's look at that. I'll just do that really quick and outline it, right? So I think I can do that, right? All right. So here we have the force in the middle, and it's pinned at the left side. All right. Now I'm going to remove the pin on the right side, and I'm going to replace it with a force. I'll leave it as force B for now, okay? And we can do this problem. This is still this problem. Well, actually, I should take that back here. Oh, yeah, I can't do that way. No, I can't. Actually, I can't do it that way. That one I can't. This one I can't do that way. Yeah, but that one is actually at a table. But anyway, so okay, I'll take that back. You know, this one I can't do because actually this case here is going to give me a problem because that one is a mechanism, right? So that's a mechanism. I would have to do it. I could do it. I would have to do this as fixed and then find the condition where the moment goes to zero. But you know what? I don't. That's kind of. I don't think it's. You know what? I think it's a little more there. Probably not going into that. But okay. But suffice to say that if you're have a good understanding about superposition, very often you can cleverly use the beam tables to get you a lot of answers that you might not have had otherwise, right? And like this statically indeterminate problem here is a good example. You know what I mean, right? The integration is not bad. It's just you just got to be real careful about the algebra. You know, it's really one thing. All right, so stop there. Okay. That's a lot on beam bending reflection, right? So that's basically everything you could imagine. Okay. Any other questions? Could be on chapter 8 or 9 or 10 as well.
Professor, about this chapter, are we allowed to use the tables during the exam?
Yeah.
Okay.
I'll probably, just stick them on the back page of the PDF of the exam. Does that make sense? I think.
Okay.
You also, no, okay, so this is a good question. Also, I do not expect you to memorize those equations for stress and strain transformation, right? I mean, they're actually not too bad, but like clearly I don't, no practicing engineer has that memorized, okay? Only professors that have nothing better to do with their time, okay? So I don't expect you to memorize that. I would give you that. That's actually in contrast to knowing like MC on I and TC on J. Those things, engineers in practice, mechanical engineers in practice, they know those things. Okay, so that's why I make you memorize those. Although I know it's online exam, so I can't control what you look up anyway. You don't have to memorize the buckling equation or the effective lengths or K values for the different end conditions. Does that make sense? I will give you that, okay? I don't expect you to memorize that. Although, again, it's really not that hard to remember. But again, people in practice really don't have that memorized, okay? Obviously, MC on I, TC on J, P over A, you know what I mean? That I is, base height cubed over 12, parallel axis. Those you should know, okay? Those you should know. TC on, VQ on IT, you should know those, right? Because those all have to go into chapter 8, okay? But the other ones I'll give you, all right? Any other questions?
Probably some stress transformation when drawing the, do you have to draw the Mohr circle?
I'm sorry. You draw what? I caught you. I missed you.
The more circle, like the
Oh, more
graph.
circle.
Yeah.
For stress or strain?
I mean, it's kind of the same, no? I mean, it's.
Well, no. Remember when you do strain, just remember you got the shear strain over 2 on the y-axis,
I
right?
will say strain because in the other one you have to divide by 2. I don't know.
No, stress you don't divide by 2. Strain is the one you divide.
Yeah, it's strain. Yeah, that one. Yeah.
Okay. What about that? Oh,
I don't know. Yeah, probably going on over a problem.
Go over a problem on that? Yeah, okay. Yeah, I can do one of those. I can do a string transformation. Those I kind of like. Those are easy. Now, again, you can do everything all the problems that I do with stress or strain transformation, you can actually do it with those equations, right? Like you can actually find the max and the principal from those equations. I just find it so much. I just find it like those I don't remember because there's no need to remember them because Mohr circle is so like intuitive, right? And you can geometrically calculate all those things from Mohr circle. Okay, so let's find one that I haven't done before. Okay, let's do this. Kind of the same. Yeah. Let's look at 1024. This is pretty much what it would be. And if you want to, you could also imagine, like, if you look at 1025, that could lead to the same question as 1024. It's just that you have to use the Rosette equations for that. And I think I did 1025 in class, if I'm not mistaken. So, but anyway, okay. Where the heck are we? Oh, okay. I'm just gonna draw. I'm just gonna write it. I'm not gonna cut and paste. All right. So you see the whiteboard again, right? Well, I'm clearing it now. All right, so this is problem 1024. And we have a pressure vessel here, like it's sort of showing it like this, like there's a riveted joint. This actually really doesn't matter, but it looks cool. So they have like a riveted joint here. This is probably like the hemispherical seam of the pressure vessel. Like it's probably like, you know what I mean, right? It probably looks something like that, right? And this is zoomed in here. They mount the strain gauge here at point A. This is A, and this is the X direction, and this is the Y direction. So X, well, it's spherical, so it's like a hoop. You know what I mean, right? Although, they don't tell you it's spherical. I guess it's different values, so it's probably cylindrical. Probably looks more like this. I'll say it's cylindrical because then that'll make it different. Let's imagine it looks like this. And let's imagine these, here we got the two seams, right? And say we're zoomed in here, okay? We're zoomed in there. All right. So at point A, we know the following strains. At A, we know the strain in the X direction, which like this would be sort of in the hoop direction, is 480 microstrains, right? The strain in the Y direction, in the longitudinal direction, is a positive 720 microstrains. Right? Remember, the micro means 10 to the minus 6th, right? And then the shear strain is, the in-plane shear strain is 650 microstrains. So the one thing that you do know from the fact that it is a thin-walled pressure vessel is that there's no stress out of the plane, okay? All right. All right, so let's look at Moore's circle, all right? All right. They want us to find the maximum shear strain and the absolute. They want to find the maximum shear strain in the XY plane and the absolute maximum shear strain. Okay, so let's draw a Moore's circle on this one. And I'll try to draw it to scale, maybe, I guess. And so I'll just do this one. All right, so on the x-axis, we put the normal strains, and on the y-axis, we put the shear strain over 2, which is the real mathematically correct shear strain. And this is, again, positive if it rotates the differential element in a clockwise manner, okay? All right. All right. So let's, okay, like if we were to kind of blow up A a little bit, right? Let's first look at this right surface here, okay? This right surface, this point here. All right, here, what's the normal strain? The normal strain is the epsilon x, so that is 480 microstrains. That's the normal strain. And then the shear strain is a positive 650. So that's going to be, you know, positive shear strain is going to shear this in the up direction, right? So that's going to want to rotate this in a counterclockwise manner. So it's going to be counterclockwise, and 720 microstrain is gamma. So that means the y point is going to be minus 720 over 2, or 360, right? Does that make sense? Why it's negative and why it's over 2? All right, so let's do that. And I wrote the wrong value because I wrote 720, and the problem says 650, so that ain't right. Because it's, I'm sorry, it's that value, right? But still, it's going to go counterclockwise, so it's minus 325, right? Because we divide by 2, and it's a negative. All right, so where is that point? We go down the x-axis 480. So let's say this is 100, 200, 300, 400, 500, 600. Probably need a little more here, I guess. 700, 800, for whatever it's worth. Okay, so 480, 1, 2, 3, 4. 480 is about there. And then we go down 325, minus 100, minus 200, minus 300, minus 400. So 325. So that's about like this. And then 480, 1, 2, 3, 4. So that puts me about here. That's 1 point. That's the purple of the blue. I'll do it in. So it's obvious what that is. It's on that face. That is the 480 minus 325, correct? Okay, now let's look at this top face for the second point on Moore's circle. All right, on the top face, you know, it's the Y strain. So here we have the normal strain is equal to 720. On this face, a positive shear strain, the stress that'll induce positive shear strain is going to rotate it that way. So that actually rotates in a clockwise manner. So that's up. So that's going to be, the y-axis is going to be positive 325, right? So where's that going to put us, right? So we're at 720, positive 325. So 500, 600, 700, 720 is about here. And now we're going to go positive, about the same amount. So that puts me about here. So that's the second point on Moore's circle. That's going to be at the 720, positive 325. And now, if we were to draw this up, right? There's the diameter, okay? We can figure out the center of the circle. This center of the circle, obviously y is 0, but it's going to be halfway between the 480 and the 720. So you can take the average of those, right? Or whatever, just figure out the difference, right? It's 20, 40, 240, right? 240 over, well, whatever. Let's just do the math. Lazy. 600, right? So this is 600, 0. That's the center, right? And then we can sketch the circle. It's going to kind of look something like this. All right. That's the in-plane Moore's circle. And we can figure out the radius, right? So we know this is 120 is this distance. And then the height here is 325. So from that, I can get that the radius of the circle is the square root of 120 squared plus 325 squared. So that is 346 microstrains. Okay. And all right. So if you wanted to get the principal strains, right, the principal strains are going to be here and here. This problem doesn't ask for those, but whatever, let's figure it out. This is the first principal strain, and this is the second principal strain. So the first principal strain is the center point minus the radius. So that is 600 minus 346. And so that is 254 microstrains, okay? The second principal value is 600 plus 346. And that's 946 microstrains, okay? Also, remember, there is a 0 strain here for the out of plane, all right? And that would give us a larger Moore's circle, all right? All right, so this point here is the max shear in the XY plane, okay? And this point up here is the max shear overall, right? All right, so we can do that, right? So if we want to get the max in plane, all right? All right, so, well, that's up here, right? And so this distance is going to be the radius. But remember,
That is the y-axis, which is game on 2. So it's actually 2 times the radius or the diameter. And so that would be 692 microstrains. Now, to get the max overall, it's the radius of the bigger circle, right? And then again, we have to multiply it by 2 because we have this strain over 2. So it's really the diameter of the bigger circle. And the diameter of the bigger circle in this case is just the second principal strain. So overall max is going to be the 946. Okay? And that's how you would do that problem. Again, you know, in the book, I think they give you explicit equations for all that stuff, but it always seemed a bit odd to take something like Mohr circle, which is a graphic thing, and then memorize equations off it. It seems kind of silly, you know? But that's, I mean, you can if you want, but that's what it is, all right? So just on the strain, be careful about the 2, right? Right? This strain value here, if you want me to figure out the number, right, it's going to be equal, right, to this radius. So the radius here, this radius is the second principal over 2, right? The radius of this bigger circle, this radius here, is actually equal to the second principal over 2, right? Which is the 946. 2 divided. Oops, I'm sorry. Okay. So this, the radius of this circle is 473 microstrains, okay? So this point up here at the very top is going to be at the center point, which is 600 positive 473. Okay, but remember, this is not the value of the shear strain. That is the value of the shear strain over 2. So we have to multiply that by 2, and that gives the actual shear strain for that point to be 946, and that corresponds to the overall max, okay? And that's what we get there, all right? It's the same thing as, you know, I do the divide by 2 and multiply 2 with the diameter in my head, but if you want to see through the steps, that's exactly what's going on, okay? All right. Anything else real quick? I don't have time to go through another problem, but if you have a quick question, I could probably try to answer. No? Okay. Well, if not, very good. Good luck on all your finals, and we will see you. We'll Zoom you on next Thursday. Okay. All right. Have a good one.